Hi goers, welcome to the Chapter 4 review video. Today we're going to talk about acid-base organic chemistry. So the first thing we have to do is talk about the definitions of acids and bases, and there are three main types of definitions, but just keep in mind that all acids and bases are going to react the same way. There are just different ways that we can use chemical logic to explain the reactivity, and that's why there are three different definitions. So Arrhenius is a guy that says that an acid is a substance that when dissolved in water is going to produce H plus ions. So substance when dissolved in water makes H plus ions. And then for bases, it's the same thing, substance when dissolved in water but makes hydroxide ions. Okay? That's just the Arrhenius' definition. For Lewis's definition, an acid is a lone pair acceptor. And the key word is acceptor. And for bases, it's a lone pair donor. And the key word is donor. Okay? So the Bronsted-Lowry is pretty much the main definition that we're going to use in this class to be consistent, but you could see Lewis come up on the test or Arrhenius, so keep that in the back of your head. But an acid, according to Bronsted-Lowry, is a proton donor. And keep in mind donor is that key word, proton donor. And for bases, they are proton acceptors. And the key word is acceptor. Okay, so we're just going to move on to the next topic. So the general mechanism for acids and bases. So over here, we have this kind of long question, so let me try and fit it. So the over-the-counter medication Tums is referred to as an antacid because it neutralizes excess acid in the stomach that would otherwise cause heartburn. Tums is predominantly calcium carbonate, which I gave the molecular structure below. Draw the acid-base mechanistic arrows between Tums and the hydronium ion. Okay, so the mechanism for acid-base chemistry is always the same. It's always going to be an arrow from the base, or the lone pair from the base, grabbing a proton off of the acid, and then that bond between the acid and the proton is going to stay intact. So, and there was a whole bunch of words, but basically I'll just draw it over here. So which one is our acid and which one is our base? So we said that the more positive thing is going to be the acid, and then the more negative thing is going to be the base. So clearly Tums is going to be the base, and hydronium is going to be the acid. So it's always the arrow from the lone pair of the base to the proton, and that oxygen is going to hold on to the electrons from the hydrogen-to-oxygen bond and do that. Okay, so that is going to be the mechanistic arrows for that, and now we are done with part A. Okay, so part B, draw the high energy transition state between Tums and hydronium, keeping in mind that partial bonds are depicted as dashes. So let's just rewrite, the basic sigma bond framework over here. So we have O minus with that O, and then this O. Okay, so O and H, so the O from Tums, where this arrow is over here, and the H over here is going to form a bond. So let's do a dash to an H, and then the bond in between, so let me just highlight that, that bond broke, so that's also a partial bond, so that's also dashed, and this all remains the same. Okay, so that is the transition state. So we can just bracket it and put that double dagger at the top. That's the transition state. So you just have to show that the bond forming step, which means the OH over here, is going to be partial bonds. That was this step. And then the bond breaking step, which is the orange, is over here. So those are also partial bonds. So that is our transition state. Next, draw the conjugate acid and conjugate base that result from the acid-base reaction in the boxes below. Okay, so that's pretty easy. So we know that Tums is going to gain a proton, so it doesn't matter which side you pick. So we can do something like that. Okay, so that is, one of the structures. And then the other one was that hydronium lost a proton, so all we are left with is water. Okay, so that's pretty much it. And then the next part says, label the molecules in the reaction scheme depicted above as the acid, the base, the conjugate acid, and the conjugate base. Well, we already said that Tums must be the base, and then that must be, hydronium must be the acid. So now, the base became a conjugate acid, so that must be our conjugate acid, and the acid became the conjugate base. And that makes sense because the conjugate acid now is able to give off a proton to a base, and then that conjugate base has two sites that can gain protons, which is what a base is, according to Bronsted-Lowry. Okay, so that was this kind of biochemical applied question. It's pretty straightforward if you get, like, the basics of acid-base chemistry. Okay, let's move on to the next section. So trends for acidity. So the concept is this. I made it really big so you all understand. Acid strength can be qualitatively analyzed by checking the stability of the conjugate base. So what does that mean? Well, the more stable the conjugate base, the more acidic the starting material was. And that will make sense in a second. So let's consider the following. Which molecule, the carboxylic acid or the alcohol, is a stronger acid? And the name kind of gives it away, carboxylic acid versus alcohol. You could just kind of use logic there, but let's prove it with conjugate base stability. Okay, so basically we know that these two starting materials are going to be our acids. Acid and acid. And this is going to be our base and our base. Okay, so what happens is that base is going to grab a proton and donate those electrons back onto the oxygen. Same thing over here. So let me just draw the conjugate base. So the conjugate base is the resulting structure from the acid. So we have this and we have this. Okay, so now why is the carboxylic acid more, or stronger than the alcohol? Well, you can see that the lone pairs on the oxygen are tied up in resonance with this carbonyl. So in the alcohol, or the alkoxide anion, there is no resonance. Resonance cannot happen because we don't have any pi bonds or lone pairs that are adjacent. So since we can delocalize that negative charge over a larger region, we are forming a more stable conjugate base, so that means that acid was stronger. So that's how we can use our conjugate base stability to rationalize our acidity trends. Okay, so there are a couple of different things that we can consider. We can consider resonance, induction, size, and electronegativity. So if the conjugate base can resonate over another molecule that can't resonate, that would automatically mean that the starting material was a better acid. Induction. If we have stronger induction or more pulling of a negative charge over a molecule, then that means that starting material was a better acid to begin with. Size and electronegativity. So we see that with increasing size, we become more polarizable, or there's more shells that are around that atom, which means that there is more space to accommodate for that negative charge. For electronegativity, the more electronegative we get, the more equipped that atom is to house a negative charge. So that's why I put size and electronegativity together, because they pretty much parallel one another. Okay, so now let's just do these ranking questions. You're pretty much guaranteed a ranking question on this exam. So for B, rank the following molecules based on their acidity. So when I'm doing these ranking questions, the first thing I do is erase the H's and put a negative charge, because that's what happens in the mechanism. So now these are all the conjugate bases of the acids. Now I want to think to myself, what are the stabilizing features that can, spread that negative charge over a larger space? Is there resonance? Is there induction? Maybe it's a size or electronegativity trend. So clearly here it looks like we're going to deal with induction. So that O- is always constant in the same space. But what's different is the substitution of these other substituents around the benzene. So we have this nitro group, which is, all the way across on the other side. We have this methoxy group, which is adjacent to the O-, and we have this nitro group again, which is now adjacent to the O-, and then we just have that plain O- to the right. So now we want to consider which one is the best one. So induction, we want to look for something that is pulling electron density away. So if you forget the Lewis structure of the nitro group, you would get this whole question wrong. So the Lewis structure of the nitro group would be something that looks like this. Okay, so notice that there is no lone pairs on the nitrogen, so that means that it's going to be basically equivalent to an electronegative group. If there were lone pairs on the nitrogen, that's actually donating, so let's just say that it was an amine, so NH2. So if we had lone pairs, basically that means I can push these electrons in, and they can basically keep getting pushed around the ring, and that's adding electrons, or adding a negative charge into the molecule. And we don't want to add negative, we want to pull the negative away. So we don't want to be able to resonate, we want to just pull. So the nitro group just pulls, it does not add any negative charge in. So that means that the two molecules with the nitro groups are immediately the best. So now we're going to consider, this structure over here. and this one over here. So basically, this nitro group on the first structure is completely, I guess, 180, you could say, away from that O minus, where the nitro group over here is going to be directly adjacent. So the one that's closer is going to pull more. That makes sense. So if you're an electronegative group and you're closer to that minus, you're going to pull it a lot more than one that's farther away. So that means that I can begin to number and say that this is the fourth, and this is the third. And now we have to think about just a plain O minus versus this O minus over here. So this methoxy group has a lone pair, actually two lone pairs on it, and they can actually resonate in and push electron density around the ring. So that's adding negative charge, so that's not good. And then if we look at our plain starting material, which is an O minus, there is no sort of, I guess, stabilizing feature besides the fact that it can resonate. So that means that this one is automatically the worst because we're adding negative charge into it, and that would be 2. So hopefully that makes sense on this benzene type acidity question. Okay, so for the next one, we're going to rank these molecules. So again, the first thing I want to do is draw the conjugate bases. So erase the H and put a minus. Okay, so the first thing we want to look at is what atom has that negative charge. Well, it's a sulfur, and an oxygen, and an oxygen. Okay, so the sulfur ones have a larger space, so they're right below oxygen, so they have a larger shell, which means they're more polarizable or more equipped to house that negative charge, so that's a good thing. Then we have the oxygen, so the oxygen is a little bit smaller, so it doesn't have enough space to house that negative charge, so those aren't as good. So the first structure, we have sulfur with a minus charge, and it can resonate with this carbonyl. So clearly this one's going to be our best one, because the negative charge is on a sulfur, and it can resonate. Okay, so the next one is just a plain sulfur with no resonance. So, the sulfur is good, but we don't see any resonance, so really not that good. The next one, oxygen. So we see that we have a negative charge on oxygen. All right, not the best, but it has resonance, and that's the key here. The fact that we can resonate is a huge deal, so that means that this would be the third one. Resonance always beats anything else, is what we say. Next, we just have a plain sulfur with a plain oxygen, so we said that sulfur is larger, so that would make that obvious. Okay, so I hope that helps with, the size and electronegativity. All right, and then finally, we're just going to talk about equilibrium. So the equilibrium of an acid-base reaction favors the side that forms the most stable products. And that should make sense. So you want to favor or do a reaction that forms more stable products. You don't want to do a reaction that's going to form unstable products. So let's use this question from an old exam. So aspirin is a drug used to treat pain and inflammation, as shown below. Aspirin is best absorbed into the bloodstream that has a neutral charge. Consider the acid-base reaction with aspirin below, labeled A through C, and lone pairs have been omitted for clarity. Okay, so the first thing we want to do is draw the conjugate acid and conjugate bases for each of the reactions below, and be sure to include those lone pairs and formal charges. So the first thing we need to do is decide what's the acid and what's the base. So for aspirin and water, aspirin has a carboxylic acid functional group. So that's a pretty good indicator that this is going to be, our acid. And this is going to be our base. Okay, so if we want to show, the mechanistic arrows for that, we can say that one of the lone pairs on the water is going to grab a hydrogen and put those electrons back on the oxygen. So that's going to look something like this. Oops. And we also formed hydronium. Okay? So that's the first one. So the second one, we have this, again, carboxylic acid portion of the aspirin, and then we just have a plain sodium hydroxide. So sodium hydroxide, remember from Gen Chem, is a really good base. So this is our base, and this is our acid. So again, those mechanistic arrows would be the same, something like that. So you're going to form something that looks like this. Plain water. Okay, so that is that question, and now we have to do the last reaction. So now we have aspirin and hydronium. Okay, so this one is a little bit tricky. So we have the carboxylic acid portion, but we also have this hydronium, and we said that the more positive something is, the more acidic. So this is actually our acid, and this is actually our base. So now, which, oxygen is going to grab that proton? And it's always the oxygen of the carbonyl that typically grabs the hydrogen. So we can, grab that proton, push it off. So the two structures that we get are something that look like this. Okay, so those are our two structures. So let me just label everything else, conjugate acids and conjugate base, because it's going to help us with the last part of discussing equilibrium. So if we started with the acid, which was aspirin, then that means that it's going to become the conjugate base. So conjugate base. I'm just going to say CB and CA from now on. So this would be the conjugate base, and that would be the conjugate acid, and this would be the conjugate acid, and that would be the conjugate base. Okay, so now we need to discuss, which one is a better, where is our equilibrium lying? So we said above, up top here, that the equilibrium of an acid-base reaction favors the side that forms the most stable products. So we have these two useful pKa values telling us that hydronium is -2, but aspirin's conjugate acid is -8. So let's just fill those in. So the pKa of this is going to be -8. Okay, and the pKa of water is going to be, or hydronium, is -2. Okay, so that should help us immediately with C. So C says, that the pKa of the right side is more acidic than the pKa of the left side. So we're always going to shift away from the more acidic thing because we formed a more stable conjugate base. Equilibrium is going to be to the left. So C is definitely a viable option for the equilibrium being towards that neutral aspirin molecule. Okay, so let's look at B. So for B, let's compare, our bases. So for this sodium methoxy group, or just this, the sodium hydroxide group versus the conjugate base of aspirin, there's no resonance with the sodium hydroxide. We just have a negative charge on the oxygen, but the negative charge on the conjugate base of aspirin can resonate all throughout that molecule. So that means that the more stable conjugate base is on the right, so that means that the stronger acid was originally on the left. So this equilibrium is actually towards the right, so B would not be a viable option. Okay? So now let's look at A. If we're thinking about the direction of the equilibrium, it's going to favor the left side because this conjugate acid, this has a greater positive charge, is stronger, and that's why the equilibrium is going to be A. Shifted to the left in A. So the best way, I guess you can say that is that the more positive charged thing is the stronger acid. So for both A and C, we see that there's a positive thing on the right side of the reaction, so that means the equilibrium must be to the left. And then for B, we see that there is, we had to do conjugate base stability. We didn't check for positive charges because there wasn't any, so we saw that the resonance is possible with the conjugate base of aspirin and not with sodium hydroxide. All right, and that pretty much sums up all of acid-base chemistry. It's not too bad if you understand the logic behind it, and I think that's it for your exam material, so good luck.